Hello friends, welcome to my channel. So in this series of videos, we are going to talk about Kahn's algorithm and its variant. So we want to use several LeetCode problems to cover this topic. So in this video here, we are going to look at problem 1136, parallel causes. So our plan is the following. First, let's briefly look at the problem statement, and then we do the coding. And when we do the coding, we are going to explain the logical details about the Kahn's algorithm. So first, let's look at the problem statement. So here we are given an integer n. So n is the number of causes. So in this problem, we are going to label the causes from 1 to n. So this is an important point to notice. And then we also given a relations array. So this gives us information about prerequisite causes. For example, we have a pre-cause and we have next cause. So we need to first finish all the pre-causes in order to do the current cause or next cause. So in one semester, we can take any number of causes as long as we have taken all the prerequisites in the previous semester. So we want to return the minimum number of semesters needed to take all courses. And if there's no way to take all the courses, we are going to return -1. So here, let me first comment. If we are able to take all the courses, so this actually corresponds to the case that this graph has a topological sorting. If we do not have a topological sorting, so we're going to return -1. So let's look at the two examples here. So in the first example, so we can first finish courses 1 and 2, and then courses 3. So this will need 2 semesters, right? So we can finish courses 1 and 2 simultaneously, and then do course 3. Well, in the second example, because there's a cycle, there's no topological sorting, so therefore we are going to return -1. So here are some constraints which we want to emphasize here. N is bounded above by 5,000, and all the pairs are unique. So with that said, we are ready to proceed. So here, as we mentioned, we are going to use Kahn's algorithm to determine if there's a cycle, and simultaneously we can get a topological order for the causes. But for the problem here, what we want to return is the number of courses, a number of semesters needed, the minimum one, right? So let's integrate this return requirement with the algorithm. So here, let me mention that the Kahn's algorithm essentially is a multi-source breadth first search algorithm. So in the search, we are going to use in degree. So let's do the coding, and in between, let's examine the logic, which is actually rather intuitive. First, I'm going to define an in degree. So here, I'm going to use dictionary just for faster retrieval of information later. So here, for I in range, so here 1 to n plus 1. The reason is the first sentence, because we label the causes from 1 to n, right? So also we want to build a graph. So here I'm going to use collections default dict. So it's a set, right? The set will store the neighbor information. Then let's look at the relation. So for start end in relations, so it means that E is a neighbor of S. So in this case, first let's do graph S. This is a set, right? So we want to add this E, and simultaneously we want to update the in degree of E, because there's an incoming edge from S to E. So we're going to increment this counting by 1, right? So now we want to do the breadth first search. So multi-source breadth first search. So here, let me use a deck. So here I'm going to use collections deck. So here I'm going to use a list comprehension. So this deck will first hold the causes without any prerequisite. This is nothing but cause for cause and degree in degree items if degree. equals 0, right? So this way we will get the initial queue. So now let's do the traversal. So first I'm going to also use a finished. So this is the courses finished. So if we can finish all the courses, it means that there's a valid topological sorting. So we just need to count the semesters. And otherwise, so we're going to return -1. So this finished is playing such a role. So now let's also use a result variable. So this counting the number of semesters, right? So the current courses in the queue can be finished within one semester, right? So this is the intuition we are going to base. So now let's do the while loop. This is the very standard. So while stack. So let me first get the length of the stack, because I know for these L courses we just need 1 semester, right? So here let's first do a for loop for the stomach index in range L. So I'm going to finish this course. So let's use node. So stack pop left, right? So then we're going to add finished. So we're going to append the node. It means that we finished this course, right? And then we're going to check its neighbor or neighbors for neighbor in graph node. So because we have finished this course corresponding to node, and then the in degree of this neighbor will be decremented by 1, right? So the in degree. So then we want to check if in degree of the neighbor is 0. If so, means that this course neighbor has no prerequisites now, so we can enqueue it. So we can do deck append as neighbor. So after we finish this course, so because this will, after this for loop, this will cost 1 semester. So we are going to increment the result by 1. So this is the main logic. So if you do not include this finished or this result and this part here, this will be the standard Kahn's algorithm. So now the logic is here. So what we want to do is we want to return the result if, right, the length of finished equals n. Otherwise, we're going to return -1. So that's basically a full solution to this problem. So before we make any comments, let's first do a test. Neighbor does not defined. So let's see for neighbor in node here. It passes the first example. Now let's look at the generic case. It passes all the cases. So here I want to make one comment. Here we used this finished. The reason we use this finished is that we want to get a topological sorting order. If you do not want to use this, you can use a counting variable, right? So each time you pop a class, you are going to increment that counting variable by 1. And then in this if condition, you can compare that counting variable with the number of courses n, right? So for actual information, let's print the finished. So this is the topological sorted list. So let's test that. For example, for this problem, you can do 1, 2, 3. For sure, the topological sorting order is not unique. So you can do 2, 1, 3 also. Or you can use some more complex example to demonstrate this point. So with that said, that's about it for this video. So you're welcome to follow up and check out other videos related to Kahn's algorithm. Thank you.